introduce what we mean by a network, what is switching, and then eventually go through different types of switching. We'll introduce what is circuit and what is packet switching. If we have a collection of nodes, a collection of nodes connected by links, that we get what we call a network. So let's introduce some terminology so we can explain the different ways to deliver data across a network. The example that I'll use, and we'll flick back to it a few times, is this network here. So let's explain the concepts using this example first. Here's an example network. Okay, what it shows is devices. These are devices here, and the computers on the outside are servers, and links between the devices. So say a cable. It doesn't have to be a cable, it could be wireless link. But for simplicity, a cable, for example, going from device A to device 4. The devices around the outside we'll refer to as stations. They're the end user devices, the things that you and I will use to access and to communicate with other users. So let's call these generally stations. PCs, laptops, servers, telephones, they're our communicating devices. So we would like to be able to communicate from, for example, station A to station F. But unfortunately, station A doesn't have a link direct to station F. So this is where we use a network. So in this example, station A has a link to this other device, device 4, and it turns out that this device 4 has links to some of these other devices, 1, 5 and 7 has a link to 6, and 6 has a link to F. So I want to send data from A to F. I need to send it through these intermediate devices. Okay? And we'll refer to these intermediate devices as nodes, more specifically switching nodes, sometimes shortly just switches. Okay? So the role of these intermediate switching nodes is to deliver the data from one station to another. So A can send the data and reach F via the switching nodes. We'll look at the characteristics of the switching nodes and the links shortly. Why are they called switching nodes? Because they need to choose a direction normally of where to send the data. Look at the paths from A to F. What's a path from A to F in this example? Tell me a path. 4, 7, 6 is one path. Another one? 4, 5, 6, so another path, and we can see we could go 4, 1, 2, 3, 5, 6. We could even go in a loop if we wanted to, 3, 5, 4, 7, 6, even longer. So we have multiple paths from our source to destination. Look at station or switching node 4. What's going to happen is A sends data. Normally a station has a single link to one switching node. So it's true in this example, A connects to just one switching node. B connects to just one switching node. C to one switching node. These are normally point-to-point dedicated links from, say, your computer to this special switching node. But the switching node may have multiple links, as they do in this case. Switching node 4 has a link to computer A, but it also has links to 3 other switches, 1, 5 and 7. So if A is going to send data, A sends to switching node 4, and switching node 4 then sends the data to either 1, 5 or 7. So we can think the path that it chooses, it switches between one of those 3. And that's where the name, that the switching node comes from. Inside here we can think that there's something that connects this, where the line where the data is coming from, to one of the 3 output lines. and it can think of it as some switch. So if we wanted to send across this path 476, the switching node, when it received the data, would switch it out to node 7. Node 7, when it received the data, would switch it to node 6. In fact, node 7 has just one option. If we send it on a different path, we could send it to 5, and then 5 would choose to send it to 6. Eventually it should reach the destination F. These switching nodes do not care about the data that's being sent across the network. A creates data destined to F. Maybe it's a file if they want to transfer, or maybe it's a part of a voice call, or an email, or an SMS. The data, from the switching node's perspective, it doesn't matter. So the content of that data is ignored by the switches. It's just treated as data, and it chooses a path to deliver that data such that it reaches the destination. So the switching nodes don't care about the data that's being sent through the network. That's a difference between them and the stations. The switching nodes normally have links to multiple other switches. They don't have to, but it's common. The stations normally have just a single link to one switching node. So you can think my computer connects into the network with a link to switch 4. With that one link from my computer to switch 4, I should be able to communicate with any of the other 5 stations. So I just have one link into my computer, and in fact with this network I can send data to B, C, D, E or F. If I had to have links for each destination, an alternative would be to have a link from A to B, another link from A to C, A to D, A to E, A to F. That would be too many links if we have a large network. So that's where the switching net becomes beneficial for the end stations. They just need one link into the network, and then we rely on the switching nodes to deliver the data to the correct destination. Although the switching nodes may have links to multiple other nodes, normally they do not have links to all other nodes, which is the case here. It's not a fully connected network. A fully connected network between the switching nodes would mean 7 has a link to all other nodes. 4 has a link to all other nodes. 5 has a link to all other nodes. That would be a fully connected network. In a switching network in practice, normally we do not have that because we need too many links. Okay? As the network grows, the number of links grows exponentially. Normally you have links to several other nodes. Because we have links to several other nodes, from any pair of stations, we typically have more than one path. We saw from A to F, we have the path 476, 456, 412, 356. In fact, we could even go around. So it's good to have multiple possible paths from source to destination. One reason is because maybe there's an error in this path. Maybe this switch fails or it's having problems. So we can send via an alternative path. Or the links on this path are busy. Many people are sending data across those links, so send data across an alternative path. So it's good to have multiple paths from any pair of stations, and that's typical. So we're just trying to introduce the characteristics of a switching network. We have stations, switching nodes, those are switches. The stations normally have a single link to one switching node. The switching nodes may have links to multiple other nodes. Last week we mentioned, and we skipped over quite quickly, multiplexing. Note that A's link to 4 would normally be a point-to-point link. It's only the data coming to and from A that goes across this link. It's dedicated for this computer. Okay? It's like the cable going into my laptop. Only my data is sent across it. But the data going from 4 to 7 may be the data from A to F. It could also, this link could also carry the data from B to E. And it could carry other users' data. Okay? So the links inside the network may carry data from multiple users. and preferably carry data from multiple users at the same time. And we know that that's what multiplexing does. Multiplexing allows us data from multiple users to be sent across the one link. So commonly inside the network, these links use multiplexing, which would allow, for example, if this link had a capacity of 100 megabits per second, A was sending to F at 1 megabit per second, then it would allow B to send to E via this same link at 1 or 2 or 3 megabits per second, so that we can share this link capacity amongst multiple users. So multiplexing inside, point to point for the stations. What have we missed? I'm trying to cover these points on the previous slide. We have switching nodes. The collection of nodes is called a network, a communications network. The switches are not concerned with the content of the data. They just forward the data, no matter what it is. The devices attached are called stations. Node to station, normally point-to-point dedicated links just for that station. Node to node often use multiplexing. They are allowed to carry traffic from multiple users at the same time. The network is often not fully connected. That is, not everyone has a link to everyone else. But often we'd like to have multiple paths. Just some general characteristics of a communications network, in particular a switched communications network. And pretty much all the networks we use today are based on these concepts. What we want to go through is how do we get data via the switches, from the source to the destination. And there are two basic approaches. One's called circuit switching and one's called packet switching. And in fact, with packet switching, there are two sub-approaches. Datagram packet switching, virtual circuit packet switching. So in fact, we'll go through three. One is circuit switching, and there are two types of packet switching. We'll define what they are and show in examples how they work. They're the ways for delivering the data from source to destination. We'll go through that today and finish tomorrow. So with a communications network, we basically have two problems. How do we deliver the data from source to destination via the switches? That's what we'll start on today. The other problem is, how do we choose the path from source to destination? Which path is best from A to F? What is the best path in this example? From A to F, you say the path from 476 is the best. Why? It probably should be the shortest path. Probably, well, that's right in that in a network, normally we choose the path from source to destination, maybe not the shortest, but generally the least cost path. We choose the least cost path from source to destination, where the cost could be physical distance, the number of links, but it could be more complex than that. For example, the delay along those links, the throughput of those links. Choose the path which gives us the best performance. Choose the path that costs us the least baht. Choose the path that avoids going through a country we do not trust, if we're looking at a wide area network. So there are different ways for choosing the best path. That topic is the next one. It's on routing. So we'll cover that later. For now, we're saying, assuming we choose some path, how do we get data across that path? Choosing the best path is later. How do we get data across the path? One approach, and let's say the traditional approach, the one that's been around for the longest, is called circuit switching. It was developed and used for telephone networks. Telephone networks have been around for, say, 100 plus years, and circuit switching has been used in those networks for delivering phone calls from your phone to your friend's phone, landline phone. This is an example of a circuit switch, okay? This is the old telephone network. What happens, you pick up your home telephone and You have from your home to the telephone exchange a line. Okay? So you're the station, you have a link into a circuit switch. And that circuit switch in the old days was a set of telephone operators sitting in that room, and when you pick up, then you say hello to the operator because it connects you into the operator. You have a line into their exchange, and you say, I want to talk to John, who's at number 1, 2 and 3. And the operator knows that John is also connected to the telephone exchange, and you see here are some plugs or some ports and some cables connecting them. One of these ports will be where your telephone line comes in. Another port will be where John's telephone line goes out. And what the operator did is just takes a cable and connects the two ports together. So they connect your telephone line with the destination's telephone line. So that's circuit switching. It's the same today, except it's just all digital. That is, the computers do this process for us. There's not a manual human operator there. It's just computers that, when you pick up your phone, dial in a phone number on your home telephone line, it sends some special signals to the telephone exchange, and depending upon the destination number, it connects your line to some output line and maybe via other telephone exchanges until it connects through to the destination. So circuit switching comes from telephone networks. Let's explain how it works. And to explain, I'll use some examples on the board which will be from our example network here. Let me just draw part of it. You don't have to draw this, you have it on your handout. It's just a subset of that network. If we use as an example wanting to communicate from A to F, then in fact there are multiple paths, but let's just focus on the lower part of the network via 476 or 456. So we want to use circuit switching to connect and send data from A to F in our example. So what happens, we have links. Let's focus on the lower path, 476. We have links from between stations and switching nodes and between pairs of switching nodes. What we do with circuit switching is we go through three steps. We establish what's called a circuit. We establish a path or a connection from source to destination. Once we establish that circuit, we can send our data from source to destination. In telephone network, the data is your voice, so the analog signal representing your voice. In a data network, then it may be some file. Okay, both can be applied here. We send the data, and then when we've finished sending data, we disconnect that circuit, terminate or tear down the circuit. Again, in a telephone network, when you hang up the phone, that disconnects the circuit between your phone and the receivers. So circuit establishment, or generally connection establishment, we establish a connection from source to destination, then we transfer the data, and eventually when we're done, we disconnect that circuit. With circuit switching, we create a dedicated path from source to destination. We have 4 links in our path. Okay, the 4 links here. What we do is, in the first step, is send some special message from the source via the switching nodes to the destination saying we want to establish a circuit. So send a message, A has just one switching node it's attached to, so must send to node 4. Sends a message, I want to, let's call it, I want to connect with F. Node 4 will receive this connect request, this request to create a connection or circuit to node F, and check if it has enough resources to support that connection. So somehow from this connect request, node 4 can determine how many resources are needed for this connection. If it's a phone call, then it's one telephone line is needed, or the equivalent of one telephone line. If it's data transfer, then possibly when A sends this connect, they say, I want to connect at a rate of 1 megabit per second. That is, once we connect, I want to be able to transfer at 1 megabit per second. Sends that to node 4. Node 4 determines, do I have enough resources to support a new connection at 1 megabit per second? Okay. Now, from the resources from node 4's perspective, it is the capacity of the links that it's going to use. Is the capacity in use yet? Is it allocated for someone else? And the resources inside the device. It's a switching, basically it's a computer. Does it have enough resources to support the connection at this rate? If it does, if everything's okay, then it forwards the connect request onto the next node in the path. In fact, it chooses the path which to send it on. How does it choose the path? That's the next topic on routing. How do you choose the best path? Let's assume it chooses this path. Sends the request to 7. 7 does the same. Do I have enough resources to support a phone call or a data connection from A to F which requires this amount of resources? If yes, it sends on to 6, and if that's okay, sends on to F, and if F accepts that connection, it will send back a response. I will not draw it just yet. Let's think about a telephone call. So here's my telephone, here's the destination's telephone. What I do is I pick up the telephone number, I pick up the telephone, dial in their phone number, the phone number of F. What happens then is my telephone sends a special signal to the telephone exchange, my local telephone exchange. And based upon the destination number, that telephone exchange knows we need to send to 7. The exchange checks, do I have enough resources to support one more telephone call? For example, this link may have a capacity to support 100 phone calls at the same time. Using multiplexing, the link from this telephone exchange to exchange 7 has a capacity to support, for example, 100 telephone calls in parallel. If the current usage is, say, 53, that is, 53 calls are in progress at this point in time, then yes, it'll accept that connection because the capacity is 100, the current usage is 53, we've got one more requested, so station 4 will accept that connection and send this special request, the blue line, onto 7. And 7 will do the same. It looks at the capacity of this link, let's say it supports 50 calls, and currently in use is 47. Then again, there's one more call requested, let's accept that, send it on to 6. So long as telephone F is not currently in use, no one's on the phone talking, then 6 will forward the connect request onto F, and that will make their phone ring. Okay? Their phone rings. When they pick up, that sends back a special signal accepting that request. Okay? So this is what happens. You pick up your phone, dial in a number. That dialing in the number triggers this connection establishment or circuit establishment. Send a special message. The switches or the telephone exchanges check whether there are enough resources to support one more phone call. If yes, that special message received at the destination's telephone, it rings. When they pick it up, that triggers a response to come back saying everything's okay, the call is accepted. Okay? And then, I'll not draw the response, but the response comes back, and then you can start talking. So you get the, so first from your phones it's ringing. When they pick up, the response comes back, your phone stops ringing, and you can start talking. And the talking is the data transfer phase. Okay? So that's an example for a telephone network. Similar applies for a data network. This isn't a telephone call, but for example, I want to transfer data from one computer to another. I need to send a special connect request. The switches need to accept that if they have enough resources and send back a response. Then I send the data through the network. So, with circuit switching, we establish a circuit or a connection before we transfer data. And when we establish a circuit, the switches check whether they have enough resources to support that circuit. Okay? If it's a telephone call, do they have enough resources to support one more call? If it's a data connection, do they have enough resources to support the required data rate, for example? If they don't, maybe here, this link has a capacity of 50 calls. Currently, there are 50 calls in progress from 7 to 6. Why? Because there are other nodes out here, other stations making telephone calls at the same time through this telephone exchange. So when A makes the request, sends the request to 4, sends it on to 7, everything's okay here, 7 would check, I have a capacity for 50 calls across this line. Currently there are 50 calls in progress. It would send back a network busy signal. It would reject that request to establish a connection. And your phone would hear some signal indicating the network's busy. Okay? So that's if we don't have enough resources. Let's assume we do. Set up a connection, and once we set up a connection, we can transfer the data. And the way to think about setting up a connection, remember these are switches. The circuit switches create, like in the old telephone exchange, the telephone operator grabs a cable and connects between one line, the input line, and the output line. Okay, it connects. And similar at the next telephone exchange, when we make that call request, we connect from the input line to the output line. And same here. Once that's done, from A's perspective, it has a link all the way through to F. It's as if it has a cable all the way through to F. Because it has a cable to 4. Inside 4 there's this small cable that connects its input to this output cable, which then goes on to 7, and then a small cable in here conceptually, and then all the way to F. All right, it's a digital circuit inside switches nowadays. Now, for data transfer, think that A sends its signal along its line, representing the data it wants to send, and that signal flows through the switches. Because we have a link all the way from A through to F, we now have a dedicated path. There's no need for any special processing in the intermediate devices. Everything's set up. Our data, specifically our signal, passes through and is received by F. Now, it's more complex because there may be multiplexing on these lines, these intermediate lines, but from the source and destination's perspective, A sends some signal representing the data, F receives a signal representing that data. From the source and destination's perspective, it's now as if there's just one long cable from A to F. So if A is here in Thailand making a phone call, F is in another country, once I set up that circuit, it's as if I now have a cable going direct from my phone to their phone. It just goes through these intermediate devices. that, when we look, maybe not today but tomorrow, when we look at performance, that impacts upon delay, in that it's as if we now just have one long link. We can do things like calculate the propagation delay and the transmission delay in this case. The switches do not process the data or the signal. They receive a signal and think they pass it through them. The signal passes through the switch 4 and comes out and passes through switch 7 and then through switch 6, and eventually that signal is received by F. That's circuit switching. In a telephone network, the signal is representing your voice. In a data network, it represents whatever data we're sending. When we've finished talking, one person hangs up the phone. That is the disconnect process. There's some special message, let's say F hangs up the phone and sends a disconnect message. And when we disconnect, the switches remove this connection. They no longer connect that input to the output. That's the general process of circuit switching, which is used mainly in telephone networks. A path is established before the data transfer begins. Importantly, the resources need to be reserved in this connection establishment process. When we set up the connection, we must check, do we have enough resources? Yes. If so, then we can proceed to the next link and so on. If we don't have enough resources, we send back a rejection message, some special message saying you cannot connect. And those resources are reserved. Now let's illustrate that from the perspective of data communications. Instead of calls, let's talk about, say, some data rate, 100 megabits per second. And let's say the link here is, well, the capacity of this link, all right, 1 megabit per second. And here 1 megabit per second. So the capacities of these two links are between node 4 and 7 are 150 megabits per second respectively. Let's say I want to set up a connection from A to F, and I require for that connection a data rate all the way through of 1 megabit per second. So again, I send a special connect request to the node 4. Node 4 checks, does this link have enough capacity? If the current reserved is 53 out of 100, everything's okay. Because I'm requesting just 1 megabit per second, it has a capacity of 100. Current reservations for other users, because there are other users using this link at the same time, is 53. Sends the request onto 7. Here, if the current usage is 48, then capacity is 50, current usage is 48. It's okay to accept mine. And it reserves, that is for this link, 1 megabit per second is reserved for my connection. So for A to F, an extra 1 megabit per second is reserved. So instead of 53, now the usage is 54 when we accept that connection. And across this link, we reserve also for A to F another 1. So the current usage of this link is 49. And we get the response back. So we reserve the resources when we accept that connection. Even if we don't use those resources, no one else can. That's the concept of the reservations in circuit switching. What that means is Let's change this. Maybe this was 49. It was 49. I made a request to, I'm requesting 1. Says OK. And reserves another 1. So in fact the current usage is, or the current reserve is 50 out of a maximum of 50. If someone else comes along, station F, we've got station F, station E comes along and wants to set up a connection, connect to some other station out here, to B, and wants 1 megabit per second, then node 7 will send back a rejection, because for this link, capacity is 50, current reserved is 50, E is requesting another 1, I don't have enough capacity. Okay, that's where we check, do we have enough capacity to support 1 more? Now the complexity comes in that A reserves 1 megabit per second through to F. My application at A, let's say I'm transferring a file, the sending rate at which I send data may vary over time. Think of when you're downloading a web page. Sometimes the web server is sending the web page to you. Sometimes it's sending nothing, because when you view web pages, you download a web page, then you read that web page. At that point in time, you're not transferring any data. So maybe you spend 10 seconds downloading the page, and then 1 minute reading the page before you click on another link and download another page. So for many applications, the rate at which the data needs to be transferred varies over time. Sometimes you need to send a lot, sometimes you send nothing. Let's say I reserve 1 megabit per second, but I'm currently sending at 100 kilobits per second. I reserved 1 because I think most of the time I want to send at 1, but at this point in time I'm sending it much lower, at 100 kilobits per second. That's 1/10 of the reserved. So this 1 megabit per second, which is reserved across this link and across this link, currently I'm using just 1/10 of that, that is 100 kilobits per second. No one else is allowed to use that leftover 900 kilobits per second. That's the point with circuit switching. It's reserved just for between A and F. Even if I'm not using it, I'm not sending data at some point in time, it doesn't mean someone else can come along and use the free capacity. Here, I need to change this. Let's say that E requires 500 kilobits per second. I'm using 100 kilobits per second out of my 1 megabit per second. So in fact, on this link, there's currently 900 kilobits per second available on this link. There's 49 other people using it, plus me, that is from A to F. I've reserved 1 megabit per second, but I'm only using 100 kilobits per second for that link. So there's 900 kilobits per second at least available. But even then, if E tries to connect requesting 500, it will be rejected, because the full 1 is reserved for my connection. Even if I don't use it, no one can use the leftover space. That's one of the disadvantages of circuit switching. The advantage is that I'm guaranteed to always be able to send at 1 megabit per second. The disadvantage is it can be inefficient, because if I'm not sending at 1 megabit per second, in theory, someone else could use the remaining. But in practice, with circuit switching, it's not allowed. Okay? So we'll see that on one of the later slides. Circuit switching is good in that we give guarantees in the amount of resources for the end users, but it can be wasteful when those end users do not use those resources. And circuit switching was developed for voice traffic, for telephone networks. And it's quite good in that case because the statistics of when people are talking, we reserve one telephone line. Most of the time it's being used. We can work out such that it's efficient in the use. But circuit switching is also used for data traffic. But nowadays, if we think of, say, web browsing, if I reserve 1 megabit per second to connect to Facebook, the Facebook server, sometimes I would use that 1 megabit per second, but sometimes I'm just reading status updates and I'm not transferring any data. So with web browsing, for example, the amount that I send varies over time. Reserving some amount would be wasteful because much of the time I would not use that reservation. So with some data traffic, circuit switching can be inefficient. And we'll see an alternative in a moment. Where is circuit switching used? In public telephone networks, when you make a phone call from home. Basically across the world, circuit switching is used. Private telephone networks. Inside this campus, in the offices, we have telephones. They're all connected in a private telephone network using some circuit switches, a PBX. So that's another example where circuit switching is used. And in some private data networks. And an example is, for example, banks. The bank as a company may have branches throughout the country and have teller machines, ATMs, in many different locations. So thousands of them need to be connected together because when you withdraw money, the bank servers need to know how much you have left in your account. Okay? So banks have in the past connected all their offices and their teller machines via their own private circuit switch network, where each teller machine creates a circuit back to some central office for the bank and transfers data about the exchanges when people withdraw and deposit money. So an example where circuit switching has been used in private data networks. Private. Telephone networks is maybe the most common example you'll hear about. Just quickly, some further examples. So this is an example. Here's a telephone exchange. Do not worry about the terminology of trunk, end office and so on. Quite simply, the blue squares think are telephone exchanges. There are 3 users connected to this exchange and another user connected to this exchange. When user A wants to talk to user B, they dial in their number, and because they're connected to the same exchange, the switch inside this exchange, it's a circuit switch, connects their line via some digital circuit to B's line, and then they start talking. Okay? And they transfer the voice as some signal, analog signal, across the line to this exchange, and then through the exchange and back to B. Okay? If someone's on a different exchange, then usually there's a hierarchy of telephone exchanges. Maybe there's an exchange for all of Bangkok, and there's smaller exchanges for different locations throughout Bangkok. So you connect into your local exchange. If you're calling user D, then it goes through some hierarchy of exchanges. So one example. And another example, again, the blue rectangles think are telephone exchanges, where you establish a connection to the destination, then transfer the data. So with circuit switching, we reserve resources for the duration of this connection. When I want to transfer my 1 megabit per second of data, I reserve resources along the path, or the circuit switches do, and that reservation is allocated to me for the duration of the data transfer. Maybe there'll be a time limit. So no one else can use those resources while I've reserved them. That can be inefficient if you reserve resources but you do not use them, no one else can use them. So it's inefficient use of the network resources. So in general, if the applications, the amount of data they want to send varies over time, circuit switching can be inefficient But the good thing about circuit switching is because we reserve resources, we're guaranteed to receive them. Imagine if you had circuit switching to the YouTube web server. What you do when you access the YouTube website, you create a circuit switch connection and you're allocated 5 megabits per second. What that means, from the YouTube web server to your computer, you can download always at 5 megabits per second. The videos flow to your computer. The quality of those videos will be guaranteed. There'll be no extra delays. The quality will not, or the videos will not pause because the data rate somewhere in the internet has gone down. You'd get this guarantee quality, which is good for some applications. Guarantee of performance like delay and data rate. That's a good thing of circuit switching. A minor thing is normally the end devices need to use the same transmission rate. That is 1 megabit per second and 1 megabit per second. Or a telephone, they need to send the same signal, send and receive the same types of signals. Means you cannot interconnect any different type of device. Because, why is that? Because if A has a line to node 4 with a data rate of 1 megabit per second, normally that means that the connection can support up to 1 megabit per second, and therefore F should be able to receive at 1 megabit per second. If it could only receive at 500 kilobits per second, then the connection from A to 4 cannot be fully utilised. So typically the devices have the same data rates or the same transmission speeds. So, for example, in the bank network, all the teller machines would have the same network interface because they'd all connect back to a circuit switch. Of course, that's not true with our computers on the internet today. And they have different speeds, and we use an alternative approach, packet switching. We'll come back to some aspects of circuit switching after we go through the alternative, packet switching, and then we'll compare them towards the end. So let's look at a different approach, packet switching. Recall, with circuit switching, we establish a circuit. Once it's connected, we send our data, and think of it as we send a signal representing that data. There's no concept of packets, which we'll see in the next approach, or headers. We just send a signal representing that data, and it flows all the way through the path to the destination. Very efficient for the data transfer. There's no overheads involved. There's no delay, or very, very small delay at the circuit switches. The signal just passes through them almost immediately, a very small delay. Another approach, packet switching. Here, when we want to send some data from source to destination, we break that data into smaller chunks called packets. And similar, we've looked at frames and messages and how we divide them into smaller parts. We take our data from our source application, divide it into multiple packets, and each packet will have some header attached to it. Okay, so we know this concept. And what we do is we transmit one packet at a time. From our source computer, I transmit, if the data was, say, 3,000 bytes, and each packet contained 1,000 bytes of data, I'd have 3 packets. I'd transmit packet 1, packet 2, packet 3. The packet switching network, the switching nodes inside this cloud, would deliver those packets to the destination. The destination would take those 3 packets, packet 1, 2 and 3, put them back together and get the original data back. Okay, so that's the concept here. There are 2 different ways for how do we send the packets through the packet switching network. So 2 different approaches. We'll go through and mention how they work, and then we'll come back and explain, well, how can packet switching offer advantages compared to circuit switching? Why use packet switching? what does using packets help with? We'll see that shortly. But first, the two approaches for sending packets through the network. One is called Datagram packet switching, and the other virtual circuit packet switching. And from the name virtual circuit packet switching, we'll see we're trying to be like real circuit switching, except we're using packets. That's the idea here. Datagram packet switching is not like real circuit switching. With datagram packet switching, what we do is the source creates 3 packets, for example, sends them into the network. The way that the nodes, the switching nodes, treat the packets is independent of any of the other packets from that application message. If there are 3 packets here, 1, 2, 3, the first node may send that first packet, then it receives the second packet. The way that it sends the second packet has nothing to do with how it sent the first packet. In particular, the path that sends it along. Let's show that with an example. This is datagram packet switching. Here we have our source computer had some data, divides it into 3 packets, just as a simple case. Sends packet 1 to the first switch, so this is the first switch. It only has 1 link, so there's only 1 switch it can send it to. Sends packet 1, and then sends packet 2, and then packet 3. The first switch should receive packet 1, then 2, then 3. The first switch, when it receives a packet, it looks. Inside the packet will be a header. So if we draw the packet, we'll have a header and some data. In the header should be the destination address, e.g. not on here but F in our previous example. So it says where is this packet going to, destination, who it came from as well, and some sequence number, for example packet 1. In the application message we had 3 packets, so this is the first packet. The next one, destination, is also F, sequence 2, and the third one will be sequence number 3 to indicate to the receiver that these need to be put back into some order. We transmit packet 1, 2 and 3 to the first switching node. When the first switching node receives packet 1, it decides to send it to some other, the next switching node. When it receives packet 2, it again decides to send it to another switching node. But the important point here is that the way that the switch processes the individual packets is independent. So just because one packet, or packet 1 will go in one direction, it doesn't mean that packet 2 will follow it. It could go in a different direction. That's what we mean independent. There's no relationship from the switcher's perspective. It doesn't really care that this is the second in the sequence of this. When a switch receives this packet, it just looks at the destination and determines where to send it next. It doesn't worry that the previous one in the sequence was sent in one direction. Okay? The result is, in this example, we send the first 3 packets to switch 1. Turned out switch 1 sent them to this next switch here, and this switch decides to send packets 1 and 2 in this direction. Okay? Packet 3 is still coming at some point in time, so one after the other. Then, when this switch receives packet 3, it decides in this example to send it in a different direction, along a different path. See, 1 and 2 going back are going along this path. Packet 3 is going along a different path. That's possible in datagram packet switching because this switch doesn't care that those 3 are related. It just treats them independently. Why would it do that? Maybe the switch determines where to send it based upon the current performance of that link. So at this point in time, the link in this direction where 1 and 2 are sent, it measures as it's currently good performance. Few people are using it, therefore let's send our data across this link. But over time that changes. Maybe slightly later it measures that many people are using this link. Therefore it makes sense to send our data on some other path that avoids where everyone else is sending their data. So it decides to send packet 3 along a different path. So that's possible in datagram packet switching. Packets may take different paths through the network. The result that we get in this example is that packet 3 arrives at this switching node before 1 and 2. Because they may take different paths, one may be shorter or faster than the other. It's hard to know. So it's possible that packets arrive at that last switching node out of order. Therefore, there's the job of the receiver to put them back into order. Okay? So that's the disadvantage of this datagram packet switching. Packets may arrive out of order at the destination, and there's two problems with that. A, the destination needs to put them back into order. That takes some small amount of processing, but not difficult. B, and the major problem, some applications we need a very short delay. If the packets arrive out of order, then let's say this is the destination. Packet 3 arrives. Then packet 1 arrives. Okay, even better. Packet 2 and packet 1. So completely wrong order, in the reverse order. Let's say this is part of a video. Okay, this is streaming video from some server to my computer. When you play back video on your computer, you need to play back the video in order. If these packets represents frames of that video, when I play it back, I need to play back 1, then 2, then 3. If I receive 3 first, I cannot do anything with it because I need to receive and wait until I receive 1. So there's some delay. I receive 3 and 2, but I cannot display them on my screen until I receive packet 1 because that portion of video should come first. If not, your video would not play back correctly. So with some applications, video streaming, voice calls, out of order packets causes problems. So that's one of the problems with datagram packet switching. Packets may arrive out of order. Packets can also be lost, not shown here. Maybe one of these nodes fails. It's a computer, something goes wrong, and for 1 second, all the packets inside are lost, are dropped, deleted from memory. As a result, some packets may not arrive at the destination, so that's possible as well. An alternative approach for packet switching is, so that was datagram approach. Eventually they put back in order and delivered to the destination. An alternative is using virtual circuit packet switching. We also have packets, but before we send those packets, in the same approach as circuit switching, real circuit switching, before we send the data, we establish a virtual circuit from source to destination. So for example, before source computer sends to destination computer, it sends a special message along a path saying I want to connect, I want a virtual circuit. The destination will respond saying yes you can, and then they'll send the data. And the virtual circuit is set up, and in this diagram it's shown as the dashed line. That is, the request went along this path, this one accepted along the same path, and now source computer sends its 3 packets, packet 1, 2 and 3, go to the first switch. The first switch knows all the packets from this computer to this destination must go to this next switch on the path. And this switch will forward all those 3 packets to this one, and so on. The packets will traverse the same path. In datagram packet switching, they may not. That's the big difference there. So they all go along the same path. And there's no problem with reordering in this case. So packets arrive in order. They still may be lost. It's still possible to lose packets if there's an error somewhere in the network. So that's the core difference between datagram and virtual circuit packet switching. Why have packet switching compared to circuit switching? Let's try and illustrate. And the main advantage of packet switching is we can be more efficient by sending packets in some cases, more efficiently use the network. We saw with circuit switching there may be cases where we make reservations of resources. If we don't use them, no one else can use them. In packet switching, that's not the case. Let's try and illustrate that. Let's focus on one portion of a network. There are many, these are two switches, switch 1 and 2. And there are some source nodes, some stations. They want to send data across this link from 1 to 2 to some destinations over here. There could be more, but we'll focus just on this switch, switch 1 to switch 2. Let's say the capacity of this link is 10 units. Let's say megabits per second. I will not write the units. 10 megabits per second. Then if we're using virtual circuit packet switching, actually no, let's start simplest. Let's use circuit switching. We're using circuit switching. Let's say A first reserves or requests 5 megabits per second, sends a request for 5 megabits per second. Everything's okay. Currently, our capacity is 10. No one is using this. So we reserve here for A to some destination. This link has, out of the 10 capacity, 5 units reserved for computer A. Okay? And that means A can send at 5 megabits per second to the destination. Everything's okay for computer A. Computer C comes along and requests four megabits per second. And okay, capacity is 10, current reserved is 5. We've got enough for another 4, so we reserve for C another 4 megabits per second. And okay, good for computer C. It can send at 4 megabits per second and everything's okay. Computer B comes along and requests for 2 megabits per second. Okay. What happens? Now B requests for 2 megabits per second. What happens? It'll be rejected by node 1 here because capacity is 10. Currently I've reserved a total of 9 for other people. I cannot not accept your request for 10. I don't have enough capacity. So unlucky for B in that case. Now, this is what is requested. Let's say the application, the sending rate varies over time. Because our application, sometimes it's sending data, sometimes it may not be sending data. Or it may be sending less than what's reserved. I may reserve 5 megabits per second, but some of the time I may only send 4 megabits per second or 3 megabits per second. Depends on what the user is doing with the application. So let's say I've reserved 5 and 4, that's reserved on this link. With circuit switching, at some point in time I'm sending here 4 and sending here 3. That is, they are not using the full that they've reserved, the full capacity they've reserved. B makes a request for 2. Is it accepted? No. So A is sending at 4, C is sending at 3, a total of 7. The capacity going out is 10. B makes a request for 2, it's rejected. It's not about how much they're sending at this point in time, it's about how much they've requested and reserved. So even if we're only using 4 plus 3, 7 out of the capacity of 10, and someone else comes along and requests 2, with circuit switching, that request for 2 will be rejected because we've reserved 5 and 4 for A and C respectively. We will not let anyone else use the spare capacity. So that's the problem, or a problem with circuit switching, in that that capacity that's unused, currently we have 4 and 3 in use, so we have 3 unused, it cannot be used by someone else. Let's look at packet switching. Similar scenario. And let's focus first on datagram packet switching. We do not send requests, we just send our packets. Okay? So we'll focus on how fast are the computers sending their packets. Let's say 4 megabits per second and at 3 megabits per second. If they're sending at 4 and 3, can switch 1 deliver the data to 2 successfully? Any problems? Capacity is 10, sending at 4 and 3, is it okay? That's okay. We send our packets. So A is sending packets at 4 megabits per second. C is sending at 3 megabits per second, coming into switch 1. Switch 1 can send out, so the total coming in is 7, the total going out, the capacity is 10, so everything's okay in this case. We'd say that from A's perspective, along this link, it's using 4 megabits per second and C is using 3. In fact, we have a 3 megabits per second spare in this case. So that's okay. If they increased to 5 and 5, it would still be okay. If, forgetting about B for a moment, if A starts sending at a rate of 6 megabits per second and C at 7 megabits per second, what happens? Datagram packet switching. A is sending packets, many packets, to switch 1 at a rate of 6 megabits per second. C is sending at a rate of 7 megabits per second. Switch can send out at 10 megabits per second. What happens? This is datagram packet switching. No concept of connect and reject. We just send our packets. What do you think may happen? Okay, we'd be able to send some of A's and B's. Let's say we treat them equally. So we've got a capacity of 10. Switch 1 sends, let's say, it sends 5 megabits per second for A and 5 for C. But what's going wrong here? What else is happening? A is sending in at 6, coming out is 5. Where's the other one? Or think of it, instead of megabits per second, think of it in terms of packets per second. Every 1 second, A sends in 6 packets. The switch sends out 5 of A's packets. Where is the other 1 packet? Where? Lost, or, so one option, throw it away, we lose it. Not good. In practice, store it in memory in switch 1. Store it in a queue, some memory. So what happens? A sends in 6 packets in 1 second. 5 of them come out because we've got enough capacity for 5 for A and 5 for C. So 1 of them would go in the queue. And from C's perspective, 7 come in, and at the same time 5 go out for C, so 2 for C would go in the queue. And they would be sent in the next second. Okay, they'll be delayed shortly, and then in the next 1 second, these 3 packets in the queue will be sent. So 3 from the queue would be sent, giving us another capacity. We've got a capacity of 10. We send 3 from the queue. We can send another 7. 7 out of the 13 coming in. So more would need to be queued. So the idea with packet switching, the packet switches store some packets in a queue. They have some memory allocated for this. If the amount coming in exceeds the amount that goes out, we'll have to queue some packets. These packets will incur some queuing delay. And that's where, and we know about queuing delay, but we haven't calculated it, but this is where it comes from in most networks, that when the incoming rate exceeds the output rate, packets can be queued. They'll have to wait some time, increasing the queuing delay, with the hope that after some time, if A and C reduce their sending rate, because remember the sending rate may go up and down over time, maybe they reduce their sending rate, so C is sending at 3, A at 6, we have some packets in the queue. Now we're at a stage where the input, 9, is less than the output, so we'll be able to start sending more packets out of the queue. So we'll eventually reduce the size of the queue until it's empty, if that's the case. So the idea in this case is that with packets, with a queue or a memory inside the packet switch, we can have times when the input sending rate, exceeds the output capacity. So long as it's not always. If it's always exceeding the output capacity, then the packets will be added to the queue will get bigger and bigger and bigger. In practice, we have a finite queue, we'd have to start dropping packets, and dropping packets is bad. So if the queue fills up, no more packets can be added, they'll be deleted, dropped. That's bad. As the queue fills up, the queuing delay goes up. But if the sending rate starts to go down, because they're changing their sending rate, then we can start to reduce the queue size, start sending more packets from there. So packet switching, at the expense of having a queue here and increased queuing delay, we can allow or cater for varying sending rates and include sending rates from our devices that exceed the output capacity for some period of time, not always, which is more suited to web browsing, data applications where sometimes you're sending, sometimes you're not sending. Because if you look at many people over time, then hopefully sometime, say, half of the people are sending and the other half are not sending, so you can be more efficient in utilising the link. In the ideal case, we'd always be sending 10 packets per second or 10 megabits per second out here, fully utilising this link. So that's where the difference between circuit switching and packet switching comes in. Packet switches have queues. With packet switching, we're allowed to send in at larger than the capacity. There's no reservation of resources. The advantage is that we can be more efficient in the use of the network resources, especially when the sending rates vary over time, when they go up and down. The problem is that the queuing delay goes up. With circuit switching, once we set up a circuit, there's no queuing delay in here. There's no queue. We just send our data straight through. So circuit switching, no delay in here. Packet switching, we have a variable delay here. Circuit switching guarantees resources. We're guaranteed to get our 1 megabit per second, no matter what others do. Not true with packet switching. There's no guarantee that I'll get 5 or 6 megabits per second. If I send at 5 and someone else, 2 others send at 5 and 5, total of 15 coming in, maybe I only get 3 coming out. So there's no guarantees with packet switching. The performance is not guaranteed, but it can be more efficient. Okay. In the last couple of minutes,